morning, students. I welcome you all for another lecture on the course Computer Architecture and Organization. So far we discussed 4 units under this course Computer Architecture and Organization. From today class onwards we are going to start the concept memory system, which comes under unit 5. In today's class I just give an introduction idea about the memory systems. I think everyone aware of that memory systems. We are using different types of memories like random access memories, read-only memories, flash memories, cache memories, the secondary memories like CDs, DVDs, floppies, like all these things. So in this unit we are going to discuss all these things in detail. So we straight away enters into the concept that is memory systems. So introduction part. You just to remember the functional units concept of a computer system. In that, one of the functional unit in the computer system was memory element. The job of that memory element was a data storage. That we know that. So my first point is like this: the computer system data storage function was performed by memory element or memory elements. Simply the memory is used to store something. So that is a data storage function. The maximum size of the memory in the computer is determined by the address lines. Yes, absolutely, it is true. The maximum memory capacity of a computer system is purely depends on the number of address lines present in the system bus. For example, a system consists of 16 address lines in its address bus. The number of addresses we can able to produce by using these 16 address lines is equal to 2 power 16, which is equal to 65,536. It is simply is equal to 64K. So that means if you make a computer system with the 16 address lines in the address bus, the maximum memory we can incorporate in that system is equal to 64K. Because each and every combination what we are placed on the address bus, that represents one memory location. That means one address is equal to one memory location. So in a computer system, the memory size is purely depends on the address lines present in the computer system. That you have to remember. Coming to the third point, the number of locations represents the size of address space of the computer. Absolutely, it is true. So here the point is the number of locations. The number of locations present in the memory indirectly or directly it speaks about the size of a memory. For example, my memory is this. This memory has total 65,536 locations. This is location 0, this is location 1, and this is 65,535 location. Total number of locations present in this memory was 65,536. Then the size of this memory I can call as 65,536 locations. Simply I can call the size of the particular memory is 64K. So the number of locations represents the size of address space of the computer. That's it. Next, modern computers are byte addressable. Modern computers are byte addressable. That means in these modern computers, whatever the memory elements are present, each and every location of memory element can hold a byte of information. That is the meaning of this. I repeat my statement. In our modern computers, we have a different memory elements. Each and every memory location of a memory element can hold 8 bits. That means your memory location can store 8 bits. So that those memory elements I can call as byte addressable memory elements. That you have to remember. So if you have a memory is like this, each and every location can hold 8 bits. That means this 0th location can hold 8 bits like this. Each and every box represents one memory element. It can hold 1 bit. Like that, here I have a 65,536 locations. Each and every location can hold 1 byte. Then I can call the total size of this memory is 64 kilobytes. That's it. Because here I have a 64k locations, and each and every location can hold 1 byte of information, so that the size of this particular memory is 64 kilobytes. That's the meaning of this. Now listen friends carefully. For example, my processor want to access some information from a memory locations. Then what it will do, how it will access the information from these memory locations. In order to access the information from the memory locations, that is purely depends on the memory organization, or how we are accessing the information from the memory locations. We are accessing the information from the memory locations by using two different methods. One method is called big endian method, and second one is called little endian method, that we are going to discuss now. The first one is big endian arrangement is used in Motorola processor. That means if I make a computer system, that computer system has a CPU as a Motorola processor. In that particular system, I can access the information from the memory with the help of a mechanism which is called big endian. It is not Indian guys, it is Indian. What is the meaning of this? You can assume this is my memory of a system which consists Motorola processor was a CPU, which is act as a CPU. This is a memory. So first location, this is 1, 2, 3 and so on. This is some 65,535 location. Total here my memory size was 64 kilobytes. Now listen carefully friends. Here I can call my memory size as 64k. That means I have a 64k locations, and every location can hold 1 byte of information. Right? For example, my data was 2030H. My aim was I would like to copy this 2030H from a location 1 onwards. I would like to copy this 2030H in the memory from a location address 1 onwards. So here my number size is total, it is 16 bits, because here the number is hexadecimal. Here the number of digits present in the number was 4 digits. 4 into 4 it is a 16-bit number. In order to copy this 16-bit number, no doubt I need 2 locations. Why? Because each and every location of my memory can hold 8 bits. So I start storing of this information from a location address 1. Here I have 2 possibilities. This is my first location, there is no doubt. My second location, it may be 2 or it may be a 0. That means if I copy the information like this, the first location is 1, second location is 2. If I copy my information in the memory like this, my first location is 1, second location was 0. So this is 2 possibilities. Here it is a big endian style. That means always the lower order byte of a data occupies higher order address. Lower order byte of a data occupies higher order address. For example, here I have a 30H and I left with 1 more byte of a data which is a 20H. Here which is my higher order byte, it is always copied onto lower order address location. So that means this 20 copied here. That means lower order byte of a data occupies higher order address location, and a higher order byte of a data occupies lower order address location. If this is the scenario of a memory arrangement, then no doubt that is called as big endian style. That means a lower order byte of a data always goes to higher order address, and a higher order byte of a data goes to lower order address. Especially this type of arrangement where we found in especially Motorola processor based computer systems. So that is the meaning of first statement. I'm already told you that this is a one option in front of us to copy this value in the memory locations. Another option is this. So this another option what we can call is little endian arrangement or little endian style. Where we found this little endian style was where the systems are designed with the help of Intel processors. No doubt in those systems we are using a little endian style. What we are doing in this little endian style, what we are already done in case of big endian style, that is exact opposite operation we performed in little endian style. Exactly what here we can do. Again you can take a same example. In case of big endian style, lower order byte of a data goes to higher order address and higher order byte of a data goes to lower order address. If you took a reverse, that means lower order byte of a data goes to lower order address and a higher order byte of a data goes to higher order address. This is the scenario we are observing in little endian arrangement. That means this 30H initialized in a location 1 and 20H which is my higher order byte of a data which is copied onto higher order address location. Now in this example that was a 2. So in this case the data was stored like this. So this type of arrangement what we can call is little endian. Where we found this type of arrangement, that means we make our computer system with Intel processors or CPUs. I hope you understand the difference between little endian and big endian. And we have one more variety of a thing, that is if you go for ARM processor based systems, in those ARM processors, they support both the type of arrangements. That means they support either big endian style or little endian style. In these ARM processors, we have a register that is the CPSR, current program status register. In that we have some specific bit is dedicated for selection of this endian arrangement. By programming of that, either you select a big endian style or you may select a little endian style in case of ARM processor based systems. So that's why here I clearly mentioned ARM processors can be configured to use either arrangements. That means either you can go and use the big endian style or you can go and use little endian style. But you have to remember the big endian arrangement purely we observe in Motorola processor based systems and little endian arrangement we are observing in Intel processor based systems. But coming to ARM, it will support both. That's the meaning of this. And coming to the next point, the data transfer between the memory and the processor takes place through the use of two processor registers usually called MAR and MDR. So whenever my processor wants to communicating with the memory, in that particular occasion, two registers of a processor definitely involved in that entire communication. One is a memory address register MAR and second one is a memory data register MDR. Now we can go and see the functions of these MAR and MDR by taking this diagram. So you can assume this is my processor and that was memory of size 2 power n by k. That means here I have 2 power n locations and every location can hold a number of bits. So here my memory size is 2 power n by k words. So when my processor want to communicate with that memory, especially it will use these are two registers. One is MAR and second one is MDR. For example, here my operation is processor want to read something. Processor want to do a read from memory. Then what it do? First, the processor has to generate an address of that memory. Because here I have a 2 power n locations. I can select only one location by generating of an n-bit address. That n-bit address transferred by processor to the memory with the help of address bus. Whatever the address of processor transferred to the memory with the help of address bus, that address where it can store internally in the processor was MAR register. MAR means memory address register. The job of this particular register is this register can hold the address of a memory location, the location which is going to communicating with the processor. So that is the job of this. Once you place an address, then what it do? Once your memory receives that address, it will activate that location and it waiting for the control signal. That control signal decides which operation or processor want to going to perform on the selected memory location. So further, as a second operation, what my processor can do is, it will issue a control signal, that is read, with the help of a control signal which is r/w bar. So r/w means read/write bar. It is a control signal. By making of this signal logic level is 1, that indicates it belongs to a read operation. Once a processor issues this signal, then your memory identifies that the processor wants whatever the data that was present in the selected memory location. Then immediately what a memory can do is, it will place that location information on this data bus. Here we know that each and every location can hold a k number of bits. So that's why those k number of bits are placed on to k bit data bus as a third operation. Later it will inform that information to processor by issuing of another signal, which is again comes under this control bus, which is MFC. That means memory function complete. Memory function complete. Once your processor receives MFC signal, that means memory function complete signal, that indicates that your memory finishes what is a task that can be assigned by the processor. Here what is the task that can be assigned by the processor to the memory? The processor wants something from a selected location, so that your memory places the address location information on the data bus. Later it will activate this MFC signal. In this example, this MFC signal and this r/w bar signal both comes under this control bus category. That's why here the direction of this is bidirectional, because r/w bar was transferring from processor to memory, and MFC signal was transferring from memory to processor. So once it receives that MFC signal, then immediately what your processor can do is, it will go and take whatever the data that was present on k-bit data bus that was copied onto MDR register. Here what is MDR? Memory data register. What is the job of it? This register can hold the information of MER specified location. MER, what it specifies? It specifies a memory location address, the location which is communicating with the processor or with the CPU. So in this case our operation is read. So whatever the data we are going to read from MER specified location, that data was copied onto this memory data register MDR. So with the help of this MER and an MDR, our processor can communicating with memory with the help of control signals. That you have to remember. Next. Here one more important thing is, the measure for a speed of memory, we consider two important parameters. One is memory access time and second one is memory cycle time. To measure the speed of memory, we consider these are two parameters. One is memory access time and second one is memory cycle time. What these two are? The first one, memory access time. It is the time that elapses between initiation of an operation and the completion of that operation. I repeat what this is. It is the time elapses between the initiation of an operation and the completion of that operation. For example, my processor is going to do a read operation on the memory. At time instant T1, it will generate address of a memory location. At time instant T1, our processor generate address of memory location. Later it will issue a control signal, and based on the control signal, the memory can communicate with the processor. Here our operation is read, so that your processor, your memory places the selected location information on a data bus. Later it will generate MFC signal. Once your processor receives MFC signal, then it will go and took a data from a memory with the help of a data bus that was copied onto MDR. Once the data was copied from data bus to MDR, it was completed in time incident T2. Now what my memory access time? The memory access time is nothing but simply T2 minus T1. So what a memory access time? Here we clearly says that it is the time that elapses between the initiation of operation. Here initiation in the sense at what incident your processor generate address of a location. Because in every time the processor want to communicating with either memory or with the IO devices, first thing what a processor can do is it will generate an address. So here the processor generate address of memory location at T1. So that is an initiation of operation, and the completion of that operation. When the operation was completed, here your operation is a read, then it will go on to get data from a data bus onto MDR register. Then we can say that my read operation was the finishes that was happened at the T2 time incident. So that my memory access time is T2 minus T1. So this is one important measure to measure the speed of operation of memory element. And second thing is memory cycle time. What this is? It is the minimum time delay required between the initiation of two successive memory operations. What is this? It is minimum time delay required between the initiation of two successive memory operations. For example, my first memory operation is read. This is number one. And second memory operation was write. Let me mention this is. So this read operation was a finishes at time instant T1. At time instant T1, read operation was a finishes. And my this write operation starts at time instant T2. The write operation is again starts at time instant T2. Now what my cycle time is? The cycle time here is T2 minus T1. Why? Because it is the minimum time delay required between initiation of two successive memory operations. So one operation is done at T1 and second one starts at T2. The difference between that two time periods we consider as memory cycle time. Now you have to remember, friends, generally let you can assume this is a T and this is a TC. Generally TC is greater than TA. Why? Because our processor can communicating with the memory, it takes much more time. Why? Because the speed of operation of your memory is low comparing with a processor. So that you have to remember here. Right. The next one. Here's an important design issue to provide a computer system with as large and fast a memory as possible within a given cost target. Or say here the design issue. For example, I would like to make a computer system. No doubt that system must have a memory element along with a CPU and IO devices. And I have a budget for making of this entire system. In that I allocate certain amount for this memory. So whatever the amount I allocate for the memory, in that cost only I must make a memory element which size is a large as well as its operation is a faster. That's the main important thing. So what our here important point is, we allocate certain amount for memory element of your system. You choose a memory such that the memory size is a high, at the same time the speed of operation of that memory is high. So we have to get that. So that is an important design issue. Right. Several techniques to increase the effective size and speed of the memory. So here one thing is, we have to increase the size as well as we need a speed. For that we are using a different techniques. In that we are focusing on a two. One is a cache memory. By using this cache memory, no doubt the speed of operation of the system is increases. And second thing is, by using of virtual memory, then the effective size of the memory is increases. There are two solutions in front of us to meet this design issue. One is incorporation of a cache memory. By incorporation of cache memory in our system, we can increase the speed of operation of the system. And second thing is incorporation of this virtual memory concept. By doing of that, no doubt the size, effective size of a memory can be increases. Those are two of our design issues while we are selection of a memory in a required cost. So that is an important thing. So what a cache memory and what a virtual memory, because these are the two important parameters we have, or important things we have to consider. So one is a cache memory. What this is? It is a small and a fast memory. It is inserted between a larger, slower main memory and the processor. So what a cache memory is? One thing, it is a small memory. Second thing is, it is a fast memory. One thing is, it is a smaller, and second thing, it is a faster. Where we can put this particular memory, I insert this cache memory in between my main memory and a processor. What's the use of that? If I place a cache memory between a main memory and a processor, no doubt the speed of operation of the system is increases, because my processor always it need not be communicating with the main memory for the information. Whatever the information your processor want, that information maximum allocation supplied by cache memory. Already we know that the cache memory is a small as well as a fast memory. Once a cache memory is a fast memory, no doubt the processor can communicate with the cache memory at a faster rate compared to main memory, so that the speed of operation of the system is increases. And second thing, it holds the currently active segments of a program and a data. What it can hold, what your cache memory can hold. Your cache memory can hold the active part of your code. That means it can hold the information which may be instructions or which may be data which is repeatedly asked by the CPU or the processor. It can hold that information in it. Once it can hold the repeated information what it can be asked by the CPU, so that your system speed can be increases. So that's what it do. And second thing, what a virtual memory is? Data may be stored in a physical memory locations that have addresses different from those specified by the program. Once we store something into a particular location, its physical address is different from that address was addressed in a program. For example, this is a different memory locations. This is a different memory locations. Physically, I assign address for these locations. This is a 2000H, this is a 2001H, and so on like this. In this location, I have a data 30H. I'm going to use this 30H data in my program. I address this 30H location with an address some 1000H. That means this same location, physical address is a 2000, but the program assigned address is 1000. That means here your program generated address is completely different from physical address. This is what we can call as a virtual memory concept. What's the use of this? How? What is the link? How we can increase the system memory size effectively? That if you are thinking in that direction, you remember friends, before virtual memory concept in the systems, what happens is, whatever the programs you are going to execute by using your computer system, that program related every information we keep in a main memory. But your processor can't execute whatever the information I have in a main memory of a program at a stretch. Your program size may be 10 bytes or 100 bytes or 1 KB or 1 MB or 1 GB. What your processor can do is, it will execute that program instruction by instruction. Then unnecessarily keep every information regarding to a program keep into the main memory. That is a useless thing. And one more important thing is, once your main memory size is lesser than your program size, no doubt that program we can't execute it by using your computer system itself. In order to overcome this, what we have to do is, we have to go and use this virtual memory concept. Once you are using virtual memory concept, whatever the information that currently we are going to use, only that portion of program I keep onto the main memory, rest of the things I placed onto the secondary memory. Once if I do this, automatically your program assign a different address, which is completely different from actual the address which are assigned to a memory location. So in this way we can increase the memory size of your computer system. So coming to the next, the memory control circuitry translate the address specified by the program into as an address that can be used to access a physical memory. Generally your memory generates an address which is called logical address. That address is completely different from a physical address. So here I need a translator, I need a circuit which taking care of this. conversion of the logical address which was generated by program into a physical address in order to access the information from a selected location. So that is the meaning of this. In such a case, the address generated by a processor is called a virtual address, or it is called a logical address. That means the program assigned address for a different locations is called a virtual address or a logical address. But your memory have an address that is called a physical address. So here our task is we have to convert a virtual address into physical address. So the virtual address space is mapped onto the physical memory where data are actually stored. Yes. Here this virtual address are mapped onto a physical address. Then the mapping function is implemented by a control circuitry. It's called a memory management unit, MMU. What's the job of this MMU? This MMU converts the logical address or virtual address which was generated by program into physical address. That's the meaning of this. So memory system considerations. The choice of a RAM chip for a given application depends on several factors like cost, power, dissipation and size. These are some of the factors. That means the choice of a RAM chip for your application purely depends on cost, power, dissipation and size. Generally, SRAMs are used only when very fast operation is the primary requirement. In your system, the primary requirement was the speed of operation. In that case, definitely I can go and use SRAMs. And the cost of this is very high, there is no doubt. Their cost and size are mainly affected by the complexity of the circuit that realizes the basic cell. Here, they are mostly used in cache memories. So, I would like to point a last point regarding to this, that is like this. If you choose SRAM for your application, no doubt the cost of that SRAM is high. Why? Because in that SRAM, each and every memory cell designed with the help of 6 mass transistors or 4 mass transistors. That means the complexity of the system is increases and the speed of operation of the system is increases, because here the memory cell can be designed with the help of purely transistors. So that here what I can say is the cost and the size are mainly affected by the complexity of the circuit that realizes the basic cell. Once this is the thing regarding to SRAM, it is very clear to us guys, we can go and use SRAMs as a cache memories of our system. Why? Because the cache memories are fast and smaller systems, we know that. And here SRAMs, what we can call is, it is a faster memories, because here the memory cell can be designed with the help of mass transistors. So that we can go and use SRAMs as cache memories of a computer system. DRAMs are the best for main memories. So SRAMs we can use as cache memories. Why? Because the speed of operation of SRAMs are very high, because the memory cell what we are used in SRAMs, those are designed with the help of mass transistors. But coming to DRAM's case, in case of DRAMs, each and every memory cell can be designed with the help of a combination of a transistor and a capacitor. Due to this, what happens is, once the capacitor is present in a memory cell, the speed of operation of capacitor is less. So that these DRAMs can be used as main memories. So DRAMs are used as main memories. The reason for this is simple. The memory cell is very simple because it consists of only a capacitor and a transistor. And the second thing is, regarding to this DRAM, the density of DRAM is very high, because a memory cell consists only 2 elements. But in case of SRAMs, the memory cell consists either 6 transistors or 4 transistors. So that there the memory cell complexity is high. And once we are using all other transistors in the memory cells, no doubt the speed of operation of that particular case is very high. That's why SRAMs are used as cache memories, but coming to DRAMs are used as main memories. That you have to remember. To reduce the number of pins, the dynamic memory chips use multiplexed address inputs. We know that each and every location can be identified with some unique address. In case of dynamic memories, what happens is, to reduce the number of pins of memory elements, we are going to go and use a concept which is called a multiplexed addressing inputs. What this is, we can discuss in upcoming classes. The address is divided into two parts. The higher order bits, which selects row in the cell array, are provided first and latched into the memory chip under the control of a signal which is called RAS, means row address select. So here, whatever the address lines I have, or whatever the address my processor will generate to select one particular memory location, what it do is, it will generate an address at a time. But that address I split it into two parts. That is divided into two parts. So one part I can consider as higher order bits of an address. The higher order bits of our address are used for selection of row of cell array. That selection of a row we do with the help of a control signal which is called a row address select. Similarly, the remaining address lines, which is nothing but the lower order address lines, the lower order address bits are used for selection of a column. Selection of column are provided on the same address bits and a latch using the CS signal, which is nothing but column address select. So what is the meaning of this? If you are thinking that direction, your memory cells are arranged in a particular matrices form. In that case, we have a row identification number as well as we have a column identification number. And whatever the address your processor can generate, that address can be split into two partitions. One partition is used for selection of a row that we do with the help of higher order bits, and the remaining part are used for the selection of a column. So for that purpose we are using a lower order bits. So this do with the help of some latches. To enable these latches, we took the help of our two control signals. For row, we have a latch that can be enabled with the help of a RA signal, that is nothing but a row address selection signal. And similarly, the latch what we have for selection of a columns, that we select with the help of column address signals. That's important. I already told you that the processor issues all bits of address at the same time. The required multiplexing of address bits is usually performed by a memory controller circuit. This is an important. That means once a processor generates an address, that address can be split into two partitions. One is treated as a column address bits and second one is a row address bits. This we do with the help of a memory controller circuit. Generally, this memory controller circuit was placed between our processor and memory chip. So where we can put our memory controller, the memory controller was placed between our processor and the memory element. So let me go and see that. Yes, this is. So this is our memory controller which can place between a processor and this memory. So in this case, the processor generates an address of a particular location at a time. That address can be received by the memory controller with the help of address bus or address lines. Once it receives an address, it will split that received address into two partitions. One partition is used for selection of a row that we do with the help of higher order bits of a received address, and lower order bits of a received address is used for selection of column. So that it will taken care of. And here there are different control signals are present between a processor and a memory controller. The first one is clock signal. So this is, let you can assume CLK, clock signal. Because our system is synchronous, no doubt we need a clock. So this is the same clock we apply to a memory also. So this is our clock signal. And second thing is, once your processor send an address, it definitely generates a control signal that indicates to which operation our processor going to perform. So for that, here my control signal is read/write bar signal. So here also the same signal, read/write bar signal. So before starting an operation by the processor with the memory, first it will inform that information to memory controller by issuing of a signal which we can call as a request. First the processor issues a request as a first step. Second thing, it will generate an address, and third thing, it will generate a control signal, and all these things are activated and deactivated with reference to clock. Once it receives this information from the processor by this memory controller, what it do is it will split this received address into row address as well as a column address. Later it will send one after another to the memory element, and the next thing is it will generate a control signal, that is read/write. And here important thing is our memory controller has to give a signal to this memory when it issues an address. If it issues a row address, that row address it will give to the memory with the help of a control signal, that was RAS, that is a row address selection signal. And similarly it will send a column address information to the memory, then it will activate a signal, column address selection signal, CS. And one more thing, this memory can accept this address as well as a clock, control signal, and these are two control signal. It is only happened this memory chip was enabled. This memory chip was enabled by receiving of a chip select signal, CS bar. These are the different signals that exist between a processor, memory along with this memory controller. So once your processor issues a read signal, then it makes logic 1. After sending of a row address, column address with the help of these control signals, it also send this read/write bar signal is 1. Then it will select the corresponding location, and the location data is placed on the data bus. Now the data can be received by our processor itself. So in this way, our processor can communicate with the memory with the help of memory controller and these different varieties of signals. Right. So this is our concept is so this is our concept. I hope you understand what this memory concept is. So we will discuss another important concept in the next class. Thank you for patient listening.